Hi, my name is Brad Frieden. I'm an engineer at Agilent Technologies. I've been involved in digital debug for about the last 10 years. Today I'm going to talk about an application. It involves an LTE IQ modulator, and we're going to look at how a system like an LTE radio that includes digital electronics as well as the RF microwave sections can be challenging to debug, and that there are tools that allow the designer, both from the baseband team or from the RF team, to have a common environment, and that is the 89600 VSA software, to analyze such signals and pinpoint the source of where a problem might be coming. What I'd like to do is show you a block diagram of this IQ vector modulator. This was a block diagram created in a tool called System View. And then I want to show you the simulation of that circuit, and we're going to create a golden standard that everything that we measure in our hardware is going to have to be at least as good as. And in the hardware, we're going to take a logic analyzer with VSA running on it, and we're going to probe inside of a Vertex 4 Xilinx FPGA where that IQ vector modulator circuit resides, and we're going to check and see, did it make the standard of that golden standard. Then we're going to look at the output of the D to A converters, the analog signals on the scope, and again bring those into VSA and see if they've met the standard. What I'm trying to create is that if I have a problem at the very output of my design, and I don't know where the problem is, I want to look at points along that vector modulation path to see exactly where did things go wrong, and then I can go in and fix them.
Here's a block diagram of our IQ vector modulator. You can see that we have I and Q signals created, so those are going to be LTE format. Those I and Q get upconverted by 4. They get root, raised, cosine filtered, and then you've got filtered I and Q, and those are a couple signals we're going to want to definitely look at and feed into the 89600 VSA software. The I and Q get digitally upconverted, and so I have a digital IF signal that drives the D to A converter and then on out into your analog and your RF stages of this LTE transmitter. So what you see here is the design of the IQ vector modulator that was created from System View. Now what I can do is simulate that IQ modulator design and then drive that into the 89600 VSA. And when we do that, we get to see what the constellation looks like, and you can see this complex LTE format here, and I'm going to be looking to see that in the hardware I match this exactly. I also have a desired spectral width, and then finally, and very importantly, there's an error vector magnitude EVM measurement that I've got to be at least as good as, and here I'm a little bit less than 1%, so that's going to be this golden standard that we've got to check against.
So let's first take a look at the filtered IQ digital signals in this design using an 16800 series logic analyzer that's also running the VSA software. So here we have a couple labels. This is the I data, the Q data, and then I also have the I and Q data in a chart mode. So I'm going to hit run and we'll capture the signals. So the hexadecimal version, not too interesting. But if I look at the chart mode, now I can see some signals that very much are what I would expect as a filtered I and a filtered Q. And in fact, if I bring that a little bit more of a macro view, I can see a classic LTE kind of signal. Now what I want to do is see in VSA what this looks like. So we're going to import that to VSA. Alright, and here is a view of those same signals but processed. I see the IQ constellation. It's perfect. It's exactly what I was expecting. The spectral width, it's correct. And the error vector magnitude, 0.46%. So if there's any argument going on between the digital guys that implemented these digital filters and the RF guys, well, there's no more argument now. It's clear up through the filtered IQ, this design is perfect. So we've seen that the digital filtered I and Q looked fine. The next stage in the design was upconverting to a digital IF. Well, we've got a probe point inside the FPGA for that DAC input. So we're going to select that. Now we have that DAC input as our signal to view, and I'm going to press run. Here is that digital view in hex of the digital DAC input signal, and if we change our time per division, there is that view through the chart mode. So it looks right. That's the kind of thing I was expecting to see for an LTE signal. We're going to look now at importing that signal to VSA. So input digital, this is where we can bring in the logic analyzer signal. There's that bus DAC input. It's a real offset binary type of format, and with that I should be able to press the run button and bring that information into VSA to view and see how we're doing. Alright, so constellation looks good. Spectral content, no problem. And error vector magnitude, 0.9%. So all the way through the digital path, we're in good shape in terms of being able to show our design has met the specification. Well, now we've shown the digital path looks fine, we need to move over into the analog world. Get through the D to A converter, and the way we're going to look at that analog IF is with an oscilloscope. So here is that signal we're bringing in by coax. It looks like an LTE signal, but I need to dive deeper into, is it meeting the specification? For that, we're going to use VSA again. So I can bring up VSA and import the scope signal into it for a final view. Alright, so I'm going to recall a setup file that I have here where I set things up for this expected LTE format. And what it'll do is it's going to import that scope capture. It's filling the time record. And the moment of truth. So, we see a constellation. It looks pretty close to right, but do you see how these individual parts of the constellation are a little fuzzier than we saw before? Spectral content looks okay. Error vector magnitude 1.15. We're beyond what we're allowing through our specification. So as we've moved now into the analog side of this design, we've got something to worry about, and we're going to have to dive deeper into what's happening. We've seen how a combination of tools, the system view at the simulation and design level, the oscilloscope logic analyzer for capturing the digital and analog information, and VSA allowed us to pinpoint where a problem is and be able to go after that root cause and fix it. If you'd like more information about these tools, you can visit the URL below. Thanks for watching.